So we are very pleased to have Professor Gillbert Strang from MIT as our Nobel winner distinguished lecturer. Professor Gillbert Strang has many prizes, and I will not sort of try to cite all of them. I just want to mention that he is a Sloan Fellow. He is a member of the American Academy of Art and Sciences. He has the Henry C. Prize from the International Congress of Industrial and Applied Mathematics in 2007. He's also a von Neumann Prize Medal winner, and he's also a member of the National Academy of Science. So it's our pleasure to have him as our speaker this year. Thank you.
Thanks. Oh, thank you. Okay, so you've had time to see that there isn't very much on that first slide. The main point maybe is just that if you have a sequence of numbers, let's say, it's a good idea. It's a wise move to make a function out of it, or make a periodic function out of it. And same thing if those are matrices, then you get a matrix function. And so the properties of a sequence, it becomes a problem in function theory, the properties of that function. And of course, one beautiful and really all-important fact for signal processing is the correspondence between convolution in the time domain, I'll say, and multiplication in the z domain or the frequency domain. And I'm thinking of these sequences as doubly infinite. Okay, so convolution multiplication, that's we know is so basic. Okay, now I guess I like linear algebra, so I think of the matrix, the tuplets matrix. So, and I'm still thinking of it as doubly infinite. So it's pure convolution. If I do a matrix multiplication, I multiply that matrix by a vector x. I'm doing a convolution of the sequence with x. I'm doing a multiplication of the z transform with the z transform of x. The basic facts. It's just nice to have this two ways to look at a problem. And the rules mean that when I multiply two tuplets matrices, again, I'm taking them doubly infinite, no issues with boundaries here. That corresponds exactly to multiplying the two symbols, which shall I call that function the symbol of the operator, and then important facts about A, like is it positive definite, translate into lower bound on the symbol. Invertibility of the matrix translates into the symbol never zero, and more than that, of course, the inverse matrix. The symbol for the inverse matrix is just the reciprocal or the inverse of A of Z. Okay, basic things that provides the tool to look in function theory. So can I just staying with here's an example. Good. Okay. So that's a tuplets matrix, and you see that I was wise enough to make it invertible. That main diagonal is bigger than the other two, so I'm okay. And then what I liked about it is the inverse has this fantastic, it's tuplets, of course, and it has this really nice perfect decay at geometric decay with the constant 1/2. So why is 1/2 the constant? Well, how do you analyze such a matrix? So its symbol, since we only have three coefficients, we have a polynomial. So when I say polynomial, I'm really meaning Laurent polynomial. It's got a finite number of terms, and one of them, of course, from off the diagonal is the z inverse term. So you the A inverse, I have to take the reciprocal of the symbol. And then, if I want to get it in detail, and since it's a polynomial, I factor it. I discover that the roots are 2 and 1/2. I can use partial fractions are useful. I actually, we teach those in calculus, and here it turns out you can actually, they simplify the issue. And that reminds me, I'm always injecting questions. The idea of matrix partial fractions, you'll see that everything is simple for scalars here. And everything becomes like that much more interesting when we have matrix valued things. And somehow, I guess playing around with this example led me to wonder, what would you do, what would be the equivalent of ordinary partial fractions with matrix functions, rational matrix polynomials. I didn't see that in the literature, and I suspect there are open questions there. Now, a part of this talk, so can I say what's sort of like the goal in the talk? The goal will be to escape from triplets, really. And so several directions of progress, but many open questions in escaping from triplets. So I'm beginning with triplets, where we can switch immediately to the function and get the answer. So, this is a fact about, so one of those topics will be about inverses of band matrices. And I had not realized, and I'm just thinking, where was I? To know, do you know that the inverse of a tridiagonal matrix, so I'm talking here in this picture about a finite one. So there must be something special about the inverse of a tridiagonal matrix. And what's special is, it's likely to be full, right? It's likely to be no zeros. But it has the fact that this has bandwidth 1, I would call that bandwidth 1, converts in the inverse, so now I'm going to the inverse of that matrix, to a property about rank in the inverse. And that property is that, say I look at the upper triangular part of the matrix and take any submatrix here, like so, the rank of that submatrix is 1. The rank of that submatrix is so this is a fact about inverses of band matrices. And since you know as well that band matrices are tremendously, they appear in all kinds of applications because the computation of each output is fast. Okay, so that's a fact about the rank, and then of course the corresponding fact will hold below the diagonal, rank 1. Maybe while I mention this one, can I say what would be the corresponding fact if it had 5 diagonals? As, for example, the Dobeschi wavelets would have. We maybe can see that. So now I've given it 5 diagonals, so you'd expect something a little different here, right? You might expect the rank to go up from 1 to 2. Or maybe I should say less or equal to 2. And actually, more than that, the submatrices go 1 across the diagonal. So that submatrix would, where's the diagonal? So it would cross it. Yeah. So, and a Swedish guy named Asplund got that picture beautifully right. Yeah. Okay, so that's inverses of band matrices. You'll see that they're coming in what come later. So that would be, I guess the point was, you can see that, do you see the rank 1 part here? So that's a half, a quarter. What would be up on the row above it? if it's tuplets, just this 2 by 2, say, would be 1/4, 1/8, right? And sure enough, we would have rank 1 there. But of course, you don't have rank 1 for a submatrix crossing the diagonal. I mean, that's overkill. Yeah. Okay. All right. So these are the basic facts then. Tuplets, if I'm thinking about doubly infinite, if I'm thinking about banded ones, then I have a polynomial. The inverse of that polynomial gives me the right thing for the inverse tuplets matrix. Products go into products. And if it's block tuplets, all the same, except it's a matrix polynomial. Now, just a word or two about the more difficult case when the matrix may be only singly infinite or even finite. So there's, you could say in a differential equations language, there's one boundary at 0 in the singly infinite case and 2 boundaries in the finite case. And of course, boundaries they're our enemy in a way. The enemy of Fourier, right? Fourier is a happy guy when there are no boundaries and everything works perfectly, just those neat correspondences, and of course it becomes not at all so simple. Well, circulants would be the finite equivalent of no boundary. When you have periodicity, then you've sort of washed away the boundary. So for circulant matrices, we're good again. But the real, I suppose, tuplets' real work was, as reflected in the early book by Zega Grenander, and then the encyclopedic work of Butcher and Silberman, is mostly about the singly infinite case. I see, happily, Wiener came in here twice. I didn't realize that, actually. I mean, I was just writing down important facts, and I guess not surprisingly. Yeah, I don't know if you know Grokenig's book on all these things. I noticed it on the table outside. It's extremely good. Right. And Grokenig has some lecture notes on Wiener's L1 lemma. Do you remember that? That if the sequence is absolutely summable, then the same, and we have invertibility, then the same is true for the inverse. Yeah. So that, and of course, many more functional analytic results. I'm more interested in that appearance of Wiener-Hopf. So what was Wiener-Hopf? That was a factorization of our symbol into a plus part and a minus part. And why was that so useful? Because it led Wiener and Hopf. It produced for them a factorization of the singly. They were sort of doing the singly infinite case, either the discrete case that I'm talking about here, or the continuous version for integral equations. So what factorization does that correspond to? Factorization is going to be a main theme now. Okay. So let's see. So it's this issue of factoring a polynomial or a matrix polynomial into, and I'm not really into plus positive coefficients, coefficients from 0 up, and times coefficients from 0 down. And that corresponds to a factorization of the triplets matrix. Okay. So maybe I write it as LU, or I could get UL. So I just want to pause a moment here to say that this factorization, this plus-minus factorization of matrix polynomials, scalar is pretty easy. You just put all the roots on, you just divide the roots. Do they belong with U? Do they belong with L? No problem. But the matrix case is another matter entirely. And it has one of the most, like I'd say, distinguished histories of problems in operator analysis, operator Fourier harmonic analysis. I don't know. The possibility of this factorization in the matrix case when the coefficients A don't commute, that's of course the source of the problem. It goes back to about 1900. Plemelj, he published a factorization. Birkhoff, that's Birkhoff Sr., who was sort of the leader of U.S. mathematics in his day. He proved it. Didn't know about Plemelj's proof, and he used differential equations. That was his area. And it was obvious, if you read Birkhoff's paper, you see he was very, very pleased with coming up with establishing this factorization. And then other people have done so since. And then, I think, but Plemelj really did it well. Probably Birkhoff's work, and I think Hilbert had a part too. I mean, it's a really major history. And in coming to our time, well, Gillbert passed away a year or so ago. I would say he was the greatest linear algebraist of his time, clearly. Yeah, fantastic. And Kaszuk is one now. He's just retired in Holland. And Spitkovsky is at William and Mary. And one reason I mention these three, one of many reasons, is they after a conference like this, they contributed about a 100-page paper about the factorization. And I found it in a very complicated subject. Birkhoff was not. I didn't learn anything much from that one. But from this one, it's really nicely written. And then, talking to Spitkovsky, I wondered if we had a polynomial. Yeah, so here's a question, which I think we could answer but didn't really nail it down. Suppose you have a polynomial. Say an ordinary matrix polynomial. A matrix polynomial. Can you factor it into linear factors? The way you would factor ordinary scalar polynomial? You would just find the k roots of the polynomial and write it out. In the scalar case, no problem. What's up with the matrix case? What are some of those things? So I guess I believe there's still some questions here, and this paper gave one of the few constructive directions for the factorization, rather than proving only existence. Okay, now to the main theme, which is matrices, often doubly infinite, because I'm not going to worry about the boundary part. What's new, or the new issue is to deal with them when they're not tuplets anymore. Not tuplets. So you could say a time-varying filter. If you think of the original matrix A, the convolution matrix, the tuplets matrix as a filter. I mean, it's such an important class of matrices, we have all these words for it. Filter, convolution matrix, tuplets matrix. Now it's going to vary down the diagonal. And you could make hypotheses that it was slowly varying, but I would like to even just deal with general, banded. So that would be my hope. To deal, what can we do with general, banded, doubly infinite matrices? How far can we carry the main facts of linear algebra to that direction? So that's really my subject, and that's in the title. I think there was the line, algebra needs help from analysis. And I'll try to show at what point maybe analysis can help. Right. So everybody understands the problem. Actually, it's just a general banded matrix, let's say invertible, bounded, put on sort of normal hypotheses. Can you factor it? Now, let me just see what comes next. Yeah. Well, this is finite, but we can translate it to the infinite case. This is like something that maybe it's really basic. So you remember the LU factorization, right? Probably even teach it. So it comes from elimination. When you do Gauss elimination, if you don't run into any special problem, the pivots are non-zero and you just go for it, you have factored the matrix into L times U. Right? That's familiar, the LU. The U is the upper triangular that you end up with. The L contains, in a beautiful way, contains all the multipliers you used in elimination to get there. And then, of course, there could be a need for a permutation matrix, because you might have to do some row exchanges if a 0 happened to show up in a pivot position or several times. So then you're faced with a question. Do you recognize when I say LPU? That's sort of like not very conventional. MATLAB would never settle for LPU. So MATLAB, which really does these problems, does many more row exchanges than strictly necessary, right? If it has a small number in the pivot, it does an exchange to get a bigger number there. But can we be algebraists? And if you're an algebraist, P in the middle seems right. And partly because in the middle there, it's unique. There's a unique P where if we allow PLU, as MATLAB of course allows, it has to allow itself because it wants to do more exchanges for numerical stability. But we're not dealing with numerical stability. Then the P in the middle is, and maybe that's associated with the name of Bruja. Can I put that name up? Just because. Yeah. So he's so Lie algebra is everywhere. That's a central fact. And actually, they are a little more fond of this upper triangular times permutation times upper triangular. Two upper triangulars. They like to have the two upper triangulars because then they can talk about the algebra of upper triangular matrices and go with it. So maybe my point is, if you ever see that this would arise if you do elimination starting at that corner. If you do elimination starting at that corner and clear out the row above it, you're doing upper triangular things, right? To take a multiple of one row from a row above takes an upper triangular matrix. So instead of the L, it's a U, right? And these are different. I'm sorry, that's quite different from that. Yeah. And then you might think, and it comes in with Wiener-Hopf. Yeah, Wiener-Hopf. The key idea. So they're doing singly infinite matrices. Singly infinite. Now, if you have singly infinite tuplets matrix, so tuplets matrices, I should say. Then if you do L times U for a lower triangular times an upper triangular tuplets matrix, the product won't be tuplets. So you've messed it up. Well, the Wiener-Hopf idea, their observation, you could say, which started them, is that if you do upper times lower, do you see that makes it keeps tuplets So my comment here is about UL is the right order, right sequence, U first, because if we have U and then we have L's, then you see when I do this multiplication, I'm catching everything. I mean, all those things multiply exactly these, and the next row these multiply these. So this is the Wiener-Hopf order to do it in. Yeah. No, it's just, and then of course doing the factorization was the job. Okay. All right. So now where are we? Well, maybe I have three directions to suggest as where have some partial progress, but not complete. And one of them is just the basic one. Can you factor into LPU, or any one of these, but let's take LPU, a doubly infinite, let's say the matrix is banded. Okay, banded, but doubly infinite. Can we factor that into LPU? It seems to me like, yeah, we would. LU and LPU are so fundamental for a finite matrix, you naturally think, what about infinite matrix? And elimination isn't going to do it any longer. Because we can't start. That's A11 is in the middle of the matrix. In a finite matrix, it's right at the corner and we go. But in a doubly infinite matrix, we can go forward from A11 doing elimination, but we left behind a very big problem in the negative quadrant. So the question is it still true? And I think the answer is yes. I'll try to say a few words about the direction of that proof. Yeah. So that's one of the problems, is to do a straightforward matrix factorization when the matrix is doubly infinite and not tuplets. You see, of course, that if it's tuplets, then the Gochberg, Plamelj, Birkhoff theorem is going to do it for you. But in the general case, not. Right. Okay, so that's one direction, LU or LPU. Yeah, and I'll say a word about where the analysis helps. Okay, so can you keep in mind one factorization LPU? Let me see what. Okay, wait a minute. Oh, all right. Second issue. So, no, I'm moving to a second question. And it connects to this banded matrices, and I'm interested, yeah, okay. So can I tell you what I'm interested in? Banded matrices, we have this nice information from Asplund about how to recognize them. And yeah, so maybe what I'm thinking is that with wavelet matrices, I always felt that especially remarkable property of wavelet matrices that made them practical is the fact that they're banded, of course, right? The Dobeschi wavelet matrices are banded, and their inverses are banded. So that's a very unusual family of matrices. Banded matrix with a banded inverse. Yeah, that's a very special kind, but wavelets are in that collection. So it's if I could focus a little while on this second question. How to describe banded matrices with banded inverses? Okay. Yeah. And so in the process, we would recover the wavelet matrices. But now because we're not, so that looks tuplets. That would be a wavelet matrix. block tuplets with, say, 2 by 2 blocks. So the Debussy matrix would fit there. Can I just recall those coefficients? So these are the coefficients for that Debussy discovered. You could say these are numbers that made her famous, justly famous. So do you remember that so what are they? The coefficients of the low-pass filter are something like 1 plus root 3, 3 plus root 3, 3 minus root 3, and 1 minus root 3. So that's a row, and this is the D4 wavelet. So this is, I'll just put D4, D for Debussy. So that's the low-pass filter. Now the high-pass filter reverses the order. 3 minus root 3, 3 plus root 3, 1 plus root 3, and alternates the sign. So minus that and minus that. Okay. And then that would be, that would give us, after the downsampling, that would give us, when it multiplies input signal, would give us one, so it multiplies a bunch of samples, and that combination would give us one of the low-pass wavelet transform coefficients. And this product with the samples would give us one of the high-pass filter wavelet coefficients. So we would be in wavelet space now after multiplying by that matrix. And in wavelet space we compress. Right? You remember the whole magic of signal processing could be put in one line. Like you start with an input signal, audio, an image, TV in time. You allow yourself to multiply by some x. Let me call that. So this was the transform. And the point was that if this x is a list of pixel values, compressing it, you can't like throw away half the pixels. But if you do a Fourier transform or a wavelet transform or some other good transform to get to y, you've sort of decorrelated the you've got something where your compression will now work. You could maybe keep the smallest, decide on some compression level and keep the largest components of y, throw all the small ones away. So here's a lossy step. So this is the compression step. And then you hopefully have almost visually all the information is still here, even though this is a much shorter vector, which you can broadcast, which you can store, and then you recover the original, or not the original, but near enough, by inverting the transform. So that's the main theme, and then you have to choose A, right? The problem that signal processing offers to mathematics is the choice of A. They preserve for themselves this secret step, y to y hat. That's you have to be a licensed engineer to be allowed to do that, right? But you can be just a math guy to multiply by A, right? Anybody can do that, right? And of course, the A's that people use are Fourier. So A could be the Fourier transform, and the FFT will do that fast, and will do the inverse fast. That's the key point. Or it could be a wavelet transform. So as block tuplets, 2 by 2 blocks, maybe many in a row, or maybe just two. So here we see two a couple of 2 by 2 blocks in a row. It's a short row because it's only D4. D6 or D8 or other great wavelet choices would be longer rows, but still two of them low and high. Right. Okay. So you see why we would want and why wavelets. So I put that in as a requirement that the inverse matrix should be banded too. The inverse matrix should be banded too, so that this is fast. This is going to be fast. This is a fast FFT or a fast wavelet transform, but we want this to be fast too. Okay. And for the Fourier transform, it's fast because the same algebra, magic algebra works there. And for the wavelet transform, it's fast because these special numbers were chosen so that the inverse would be banded also. And maybe in the beginning of wavelet world, we looked always for orthogonal A. Orthogonal, of course, if A is orthogonal matrix, then A inverse is just the transpose and therefore still banded. So you get the bandedness for free if you go for orthogonality. But once to preserve sort of left-right symmetry, orthogonality can't do it. So a lot of to keep that symmetry, visual symmetry, people invented biorthogonal A, but they always chose it so that A inverse was also banded. Okay, so maybe I just want to say, well, this one is actually orthogonal, but the general rule, maybe it's here. Okay. Oh yeah. Here's the rule, and it comes from Asplund, but it's expressed in a constructive way here. So this matrix is tuplets, as I've written it, and banded. And the question is, when is its inverse? When does its inverse look the same as that? And the answer is that these blocks should have rank 1. They should be singular. Those are 2 by 2 blocks. And if you go back to Ingrid, you'll see that that this thing, the determinant is 0. If you multiply that, well, I guess I sure hope it comes out 0. It's too late to change, right? And then this also 0. So these would be the alpha blocks, and these would be the beta blocks, and that's the test. If you puzzle out Asplund in this relatively simple case, it turns out that the test is alpha and beta should have rank 1. Yeah, maybe we can see that. Yeah. Oh, yes. Well, I'm now getting a little. Okay. Can I just say what's going to happen first, and then give some detail if you would like. The rule is the same if it's not tuplets. If I have a bidiagonal 2 by 2 blocks sitting next to each other, but this is alpha 1, this is alpha 2, alpha 3, they're changing, time varying wavelets, and the betas are changing too. The test is the same. The test is the same. All the alphas and all the betas should have rank 1. It comes from this Asplund business. Yeah. So we now have the possibility. So this is my second area. The first was LPU in general. The second is looking at this special property of banded inverses and asking, how can we get that in the non-tuplets case? How can we create time-varying wavelet transforms? And the answer is, we just have to preserve this rank 1 property of the blocks. They don't have to be the same. So we could change them as we go. Okay. So that's a fact about this particular family, but I'm really interested in the whole family. of banded matrices with banded inverses. Yeah, I won't do... here is the key idea. The key idea is, we'll stay with this example. The key idea is that if this is rank 1 and that's rank 1 all the way down, they could vary, then I can factor it into block diagonal times block diagonal. That's the algebra theorem. That if these are rank 1s and those are rank 1s, then, well, and it's actually, in this case, just as straightforward. You can say exactly what these blocks should be. And now, there's something special about those two block matrices. They're 2 by 2 blocks. They're block diagonal. So, they're inverses. What do we know about the inverse of this? Block diagonal matrix, to invert it, you just invert block by block. So the inverse matrix will also have that block diagonal form. Same here. Block diagonal, the inverse matrix is block diagonal. When I multiply a block diagonal times a block diagonal, I get a block bidiagonal. Now there's that sentence concealed the key point. Can I repeat it? If I multiply a block diagonal by a block diagonal, what do I get? Well, if those blocks are in the same positions, I don't get anything much, right? If I have a block diagonal matrix, can I just do it here? It's like going to be boring, right? Block diagonal here, block diagonal, so on. If I have another one that looks just the same, then the product will be that block times that block. It'll just be the same, nothing new, nothing interesting. But so here's the key. If you offset one, does your eye show you that the two factors are like a row and column offset from each other? Then, so that if I line up over here, I get the last row of that block and the first row of that block. If I look over here, it multiplies the first row, the last row, and then the first row, and those give exactly the alphas and betas that we want. Yeah. So that's the theorem then. That if these all have rank 1, then I can factor it in that way. And then the main theorem is that oops, let me go back. Oh, there's an actual multiplication just to show that it really works. And of course the inverse works too because it's a product of the block diagonal inverses and they're still offset. Yeah. So can I, on this second topic, if it'll go back. Yeah. Okay, so this is the theorem about if A and A inverse are both banded, what can you say? And the answer is you can factor it into block diagonal. So that class of matrices is somehow, we can get our hands on it because we know about block diagonal matrices, and the product is the general one. Okay. Okay. This is still algebra, by the way. I haven't told you. I mentioned that we needed some analysis idea for A equal LPU, the first area, and also the third question. Let me come to the third. Yeah, so this is the details of that. Okay, third question about doubly infinite matrices. So we have A equal LPU, we have banded with banded inverses, and now here's a question. Which diagonal is the main diagonal? And the example that we should have in mind is a shift, because of course that's the... Somehow, I mean, Gillbert, the great man, said, take any diagonal. You know, they're all okay. And so if we have the shift matrix, so this is That's the subdiagonal there. So, and remember, it goes to minus infinity and to plus infinity. So that's the shift. Okay. Then what is the inverse of that shift matrix? Is it invertible? Sure. It's banded with banded inverse. But its inverse is upper triangular, right? The inverse of the forward shift will be a backward shift. And that means trouble in some... It's not what you want, right? You would like the inverse of lower triangular things to be lower triangular. In other words, the main diagonal belongs... That's the main diagonal, the one with the ones. Clear. Right. That's the main diagonal that has the ones. Okay, so for that particular permutation matrix, so that's a permutation matrix. Every row, every column has a single one. And its main diagonal is not the zeroth diagonal, not the one with the zeros, but it's the one with the ones. Okay. Do you see the question there? Which diagonal is the inverse? Suppose if I went back to that 5 minus 2 example, tell me which is the main diagonal for this guy. So that was we had 5s down the diagonal, we had minus 2s above and below. And which should be the main diagonal of that matrix? You believe, right? Which one? The one it's got, right, the 5s. Yeah, that's the proper main diagonal for that. Everything was perfect for that matrix. Here, the inverse is upper triangular, not good. And if we tried to compute by chopping off the problem, suppose we chopped it off there and chopped it off here. The finite section method, that would be called in this area of operator theory, the finite sections, where you just you converge, you hope, to the infinite the solution of the infinite system by growing finite systems, but of course it'll fail completely. We got it's not centered right, the diagonal's wrong, the matrix is totally singular and hopeless, right? So I guess we would like to know the main diagonal, because then we could center the matrix properly. The finite section method would work. The inverses of triangular would be triangular of the same kind. That would be good. So that's justification maybe for the question for this third question, which is the diagonal. So problem there, we see the problem, and here's the answer that's come out of a group of people, many of them in Germany, and let me try to get a name here. Marco Lindner has a couple of books on this growing area of doubly infinite matrices, and with this as an issue. And now I'm ready to say, what's the analysis idea that helps in these infinite matrices? What's the analysis idea? It's this one of Fredholm's idea of his index. Do you remember the index of Fredholm? No, that didn't move. Okay. The index of a matrix is the dimension of its null space, the number of solutions to S plus X equals 0, minus the dimension of the null space of the transpose, or the codimension of the range. That difference of dimensions is like the right thing. And why is it the right thing? So that's analysis question, and maybe this tells us this has this great property that the index of a product is the sum of the indices, good. And it also, I see it and write that key fact about the index. So that index is a number. And, well, there's a whole world of index theory now at very, very high level. But the Fredholm proved the facts that are essential here, the basic facts. And the basic fact is that you can change a finite number of entries in the matrix and the index doesn't change. Or you can, to say it more professionally, more mathematically, you can perturb by a compact operator and the index doesn't change. So that's the tool that allows you to say, well, yeah, I'll just express this thought here, giving. So here's the tool that this group, Linder and many others, use now. The key idea is we have this doubly infinite matrix, banded, and then we maybe chop it off here, and we look at the singly infinite matrix below, and we compute its so this is the matrix A plus here, the positive direction of the matrix, and we compute the index of that thing. And now the neat fact from analysis is that that index is the same for the next one. The index doesn't change. You see what I'm saying? The cutoff matrix, the truncated matrices, all have the same index. It's the right quantity, and that index tells you where the main diagonal should be. Tells you a lot if you can compute it. I mean, so they have a beautiful theorem that this index tells you everything, but then the job of computing what that index is far from simple in a general banded matrix. Far from simple. It's sort of the index is determined somehow at infinity. Yeah, but this helps with elimination. This sort of says that each step of elimination. Well, I won't try to repeat that argument here, but it's the key idea in that LPU bit. Yeah, so this index that's the analysis, the Fredholm analysis that comes in. Okay, so that's the third problem, and then the result was that this index is very hard to compute for a general matrix that's doing, God knows what as you go to infinity. But if it's a permutation matrix, you can find this index. So we just thought, okay, this is a complicated thing to compute, this index. Let's take a simple matrix, simple class of matrices. We can do it for those. And those matrices were permutation matrices, banded permutation matrices. So this is a neat little group of matrices. Banded permutation matrix, doubly infinite, banded. So if you multiply them, they're still banded. If you invert them, still good. So it's a little group of matrices, and you can find the index by just from a finite number of rows, from 2W rows if all the ones are in a band of total width 2W. It's a very simple theorem, but just a small start in about when you could find this index nicely. And of course, learning more about these, those are the matrices P and the LPU that I mentioned. So those were the three parts, and I see I'm over. Anyway, those are the three directions: LPU, banded with banded inverse, and possible applications, and index. Will you allow me to take 30 seconds more to ask you for a favor? Because I don't know if you're artistically inclined, but there's a book coming on GPS, as it happens, global positioning. And the cover has been, I was quite happy with this cover. So I'll put these down by the posters and ask for your help, because now the artist gave me another cover, which is red. And I'm just hoping, like, if you'll vote tell me which one should I use, green or red. They also gave me blue, but to hell with blue. I don't, that comes third. But I really don't know. And I asked Tom Gresso, the Berkhäuser man. He had a very definite opinion. So if I put those there with a little piece of paper, would you vote green or red? I mean, if you happen to see it. And if you're an artist, and therefore your vote is more meaningful, I mean, like worth listening to, put an asterisk or something indicating, yes, this vote should really be counted. Anyway, good. So thank you, and I'm sorry.